Good evening, everybody, and welcome to Lecture 6 in this series on cosmic revolutions. The title of tonight's lecture is Life in the Universe. In the popular American science fiction program, Star Trek, which began in the 1960s but was set in the future, each episode of the program began with William Shatner playing the hero character, Captain James T. Kirk, intoning the words, "Space, the final frontier. These are the voyages of the Starship Enterprise. Its 5-year mission to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no man has gone before." And that split infinitive captures the exuberance and excitement and the spirit of adventure that people in the 1960s thought that the space race was going to lead to. I'm not overly familiar with this particular cultural genre, but roughly speaking, Star Trek is about a modern 21st century romantic idealized version of the battle between the American cowboys, who were roughly good, and the uncivilized Indians, who were roughly speaking bad, at least according to certain cultural genres. But in Star Trek, it's given a modern, futuristic twist. But I think it reminds us that although the public have a great fascination with searches for extraterrestrial life, it's perhaps a bit problematic to reflect on the behaviour of humankind towards other species, many of which are now extinct. We have a poor historical record of behaviour towards other species. And also the historical record of our behaviour towards different cultures within our own species is again poor. There has been brutal genocide, even as recently as today. Economies have been built on slavery, slaves being people who looked different. So I think the whole prospect of searching for aliens is an exciting and an intriguing one, but I think we do well to reflect on ourselves as we venture out further and further into space. More of that later on. Humans have wondered for a long time, where might there be extraterrestrial life? And so it was natural to look for life on one of our nearby planets, on Mars. Mars is a red dot in the night sky most of the time. And a couple of centuries ago, Schiaparelli was convinced that there were canals on Mars, channels that pervade water and therefore were suggestive of life. This idea was popularised, but it seems to have become clear that probably that was a lot to do with the eyesight and the interpretation, the visual acuity of some of the individuals involved, even though it was absolutely true that even over a century ago, with a relatively large telescope for the time, careful observations revealed beyond doubt that there were geological features that somewhat resembled certain geological features here on Earth. Mars is a planet that you can observe relatively easily from Earth. These are some images from my back garden in Oxfordshire. But that's a long way away from Mars, I have to say. To get a really good look at Mars, what you want to do is to use the new NASA's new Explorer, Perseverance. And this is an image of Mars, or at least part of Mars, taken just yesterday. As you can see, it's quite a rocky place. The Mars Perseverance rover, you can think of it as a go-kart with GoPro cameras attached, is exploring Mars. It's seeing what's there, and it's drawing analogies between how similar it is and is not from planet Earth. Here are some other images taken by the same camera on that Explorer. And you can see that it's a very arid, dusty place with lots of pebbles, but nonetheless sweeping landscapes. Could there be life on Mars? Well, I think it could be difficult for life to be sustained on Mars. One of those reasons is that Mars is thought to have chaotic variations in what is known as its obliquity. The obliquity of a planet relates to the angle that it spins around. And if that flops around all over the place, you don't stand a chance of having stability of seasons, which are crucially important for sustaining life, if you think that life might need food, and I'm sure we all agree that that's important. Varying obliquity that flops around is not a showstopper for life, but it's certainly suboptimal for fledgling life to emerge. Although it's been very exciting, the images and the data that have come back from NASA's new Mars Explorer, it's interesting to speculate what might be seen if humans could actually get to Mars. But of course, there are showstoppers involved with that, not the least of which is the considerable cost. And that is something of an understatement. The cost of a crewed mission to Mars would be comparable with the GDP of a small nation. And I put it to you that that isn't quite the right use of funds at the present time. An equally important showstopper is the considerable risk that would be associated with landing on Mars. And I don't just mean the landing, which one might hope could be reasonably gentle. What I am talking about is the risk due to radiation poisoning from the sun. Mars lacks a magnetic field. Earth, thankfully, has a magnetic field, and that protects us from the solar wind and from the radiation poisoning associated with that. More of that in a moment. What about life in another part of the solar system? So not Mars now, but how about a moon orbiting around Jupiter or perhaps Saturn? Well, it's quite interesting to speculate whether a suitable moon might be found. If you're talking about a moon that's orbiting around Saturn, then although it's in orbit around Saturn, Saturn is, of course, in orbit around the Sun, and thus the distance of any of Saturn's moons with respect to that of the Sun is reasonably constant, giving you a reasonably constant temperature. So maybe it's possible. And people have speculated that maybe Enceladus, which is now the frame of reference in which this movie is being viewed, might be such a location. No mission to explore Enceladus has yet arrived there. That's the Milky Way going past and the Magellanic Clouds and the Moon. But it is interesting to speculate whether or not Enceladus, that moon in orbit around Saturn, might be suitable for habitability. So I want to turn now to what are the necessary ingredients for the habitability of a planet. Let's go through a number of these in turn. I've somewhat whimsically referred to these as creature comforts, but these aren't creature comforts in the sense of luxury items that it's nice to have to increase comfort in one's living, such as a soft pillow or something like that. No, this is definitely a bit whimsical, because I would say that these so-called creature comforts are things that are necessary for life. And one of those things that is necessary is a firm foundation. A rocky planet, a terrestrial planet, having at least some rock, much like planet Earth. Yes, there's loads of oceans sloshing around, but there's plenty of rock too. That firm foundation is great for life to inhabit in principle, in a way that a gaseous planet, such as Jupiter and Saturn, is manifestly not. It's perhaps worth pointing out that the terrestrial planets are in something of a small minority of the exoplanets that have been discovered so far. Exoplanet, of course, signifying a planet that's outside of our solar system. What are the other creature comforts or requirements for habitability? I would say that a comfortable temperature is of fairly high importance. On the planet in the solar system nearest to the Sun, Mercury, temperatures can exceed 400 degrees Celsius, which is way hotter than in one of our Earth ovens. We would not survive in such temperatures. In contrast, the temperature on Pluto, one of the most famous dwarf planets, which is sometimes outside of Neptune, sometimes inside, the temperature is minus 230 degrees Celsius, which is way lower than the temperature at which nitrogen liquefies. And of course, the majority of our atmosphere is made up of nitrogen. And so it would be pretty disastrous to have an atmosphere that wasn't even gaseous. So tuning the temperature to be about right, I think, is critically important. Planet Earth is in what is technically known as the Goldilocks zone. Not too hot, not too cold, but about right. On the theme of having the temperature being about right for habitability, a stable thermal environment is key as well. So what might give you a stable thermal environment? Well, high up on the list is the fact that the orbit of that planet around its mothership star is fairly circular, as opposed to fairly elliptical. If you had a fairly elliptical orbit, then at times in the orbit, when the planet is closer to the star, it would be a whole lot hotter. Whereas at times when the star is much more distant from the planet, at apastron, then the temperatures would be much, much lower. Stability in temperature could not be attained if you're talking about a planet with a highly eccentric, a highly elliptical orbit. I'm showing a cartoon now of a cartoon movie of two stars in orbit around one another in the frame of reference of their centre of mass, their barycenter, and you can see that at times of the close encounter, the closest approach, the periastron, there is a very significant fly past, in contrast with apastron, when they're maximally separated. This wouldn't just give you an unstable thermal environment, it would cause serious seismic activity as well. This orbit, I should say, is fully obeying Kepler's laws, as I described in my previous lecture in the series on cosmic concepts called Shapes of Freefall. Orbits that obey Kepler's laws span a continuous range in eccentricity from 0 for a perfectly circular orbit, which would give you maximum thermal stability, up to and beyond 1. I love to study stars in eccentric orbits, and that's something that I study very frequently with my Global JetWatch network of telescopes, which monitor via spectroscopic monitoring different stars that are in these different sorts of orbits. And one such star, known as GG Carina, has an orbital eccentricity of a half, and so its orbit strongly resembles the cartoon movie that I showed you a couple of slides ago. GG Carina is contained in that pink square over there. You can see three stars that are a little brighter than the others around it. GG Carina is the one nearest of those three, nearest to the top bar of that pink square. We've been monitoring it successively with using spectrographs attached to the telescopes and looking at how the spectra change every single time we observe it. This is time-lapse spectroscopy. And as we measure the wavelengths of some of those emission lines in the spectra and then say, gosh, I wonder how you've changed today with respect to how you were yesterday and the day before yesterday, which is what time-lapse monitoring is all about, then we see very clear wiggles indeed. We see clear wiggles on the timescale of the orbital period, the time for the stars to do their dance around, resembling that movie from a few slides ago. But we found another periodicity in the data as well. The orbital period is very similar to an Earth month, being 31 days, but we discovered another periodicity of about a day and a half. And we could see this in all different ways in which we investigated the data, in the wavelength shifts of some of those emission lines in the spectra, in the brightness of the star system. And what we found was that if you looked at periastron, that moment of closest approach, you would see maximally enhanced variability on that 1.5-day periodic timescale. What was going on? Well, it turns out that that flypast, that close encounter of the two stars, would so gravitationally distort the primary star in that system that it would wobble. Now, the following analogy is not exact, but it is instructive and illustrative, I think. If you take a panna cotta and you wobble it, and you notice the frequency at which it wobbles or rattles, that's because you've applied a distorting force to it. And that's kind of what happens when two stars do a flypast, a close encounter at periastron. And if you start causing those asteroseismic variations in a star, you'll cause the variations within that will cause changes in density, which will cause changes in opacity, which will cause changes in luminosity, in brightness, and hence in temperature on any planet that's orbiting either one or both of those stars. It is fortunate for us that the planets in the solar system, and crucially Earth's orbit around the Sun, is very close to circular. It's not a perfectly circular orbit, but it is nonetheless quite close to being circular. Most of the extrasolar planets, the exoplanets that we know today, have significantly more eccentric orbits than ours do here in the solar system. And so our solar system does seem to be a little bit special in that regard. But back to the theme of needing a stable thermal environment for the habitability of any planet. I've already indicated in the context of Mars and its varying obliquity that thermal stability does require a stable spin axis if you are to have stable seasons. That's a stable spin axis with respect to the star that the planet is in orbit around. Day and night are considerably advantageous to avoid overheating, local overheating on the planet. I've been working in South Africa at my observatory there the past week or so, and during the day it can be really very hot, even though we're approaching winter in that part of the world. Sunset comes as a great relief when the temperatures get cooler. Day and night are most important for comfort, I would say, for living creatures. What the obliquity of a planet is can depend on initial conditions. It can depend on something impacting the planet subsequent to its formation. In the case of Earth, we do have a fairly stable spin axis. It varies a little bit with something that's a phenomenon known as Chandler wobble. There is, in fact, a nutation superimposed on the precession of the equinoxes, but it's fairly subtle and it doesn't wreck up the stability of seasons. But if you can imagine, if we didn't have that stable spin axis and the ice caps, the polar ice caps, flopped around because the spin axis of the planet wasn't stable, we would not be able to sustain stable seasons and thereby stability of crops and hence food for the inhabitants of Earth. The moon is a great asset. It's thought to be a great asset for planet Earth, that it helps stabilise Earth's spin axis. And indeed, it gives us tides, which have been suggested by some to be important for the origin of certain types of life on this planet. So this is the famous Earthrise image of Earth rising over the moon, as imaged by the astronauts on board Apollo 8. This famous image was taken on Christmas Eve of 1968, a reminder of the closeness of Earth with respect to our nearest celestial neighbour, the Moon. Continuing the theme of a stable thermal environment, a planet that has a stable thermal environment will be a planet that has what physicists call a high heat capacity. Now, heat capacity is sometimes known as thermal mass. A low heat capacity means that just a small amount of heat will give you a large increase in temperature, whereas a high heat capacity means that you'll get a very small change in temperature even when you pump in lots and lots of heat. And you need that if you're going to have a stable thermal environment. And so the oceans are a really important asset for us here on planet Earth, because water has a relatively high heat capacity. There is lots of thermal mass in the oceans. We're familiar, I think, with the idea of heat capacity as something that's important for building design. Greenhouses are terrific if you want to grow tomatoes. The greenhouse effect is a thing. We like hot greenhouses because tomatoes like to grow in a Mediterranean climate, and in the British culture, then greenhouses will attain that for us. But in terms of humans thriving, forget tomatoes, in terms of humans not just surviving but thriving in Mediterranean and more equatorial places, you need a building with lots of thermal mass, a high heat capacity if you're going to have a stable thermal environment. Also continuing the theme of a stable thermal environment is the number of stars that a planet is orbiting around. Having one star to orbit around is about the right number. But we do know that circum-binary orbits are a thing. I spoke about these in my previous lecture on planetary universe. And just as most exoplanets that we know about are in eccentric orbits, which are not favourable for habitability, a significant number, very much a minority, but a significant number, appear to be in circum-binary orbits, the exoplanets orbiting binary star systems. But one is a really good number for habitability. What else is on the list of creature comforts that are part of our requirements for habitability? I would say clean air is up there. We need a certain amount of oxygen. The oxygen that we have in our atmosphere is diluted by the relatively inert nitrogen, which forms the dominant component of Earth's atmosphere. The oxygen that we breathe, hope no one's squeamish here, was generated a few billion years ago by bacteria that were alive on the Earth, significantly in advance of sentient life. A runaway greenhouse effect, where you've ended up with loads and loads of carbon dioxide in the atmosphere, would not be good for life. And so no one is talking about searching for life on Venus, where it seems there has been, where there is a huge amount of CO2. What else do we need for habitability of our planet? It needs to be radiation safe. As I indicated in the context of Mars, if a planet lacks a magnetic field and then it's blasted with the solar wind, which consists of essentially radioactive particles with relativistic energies in many cases, you're probably going to die fairly soon from radiation poisoning. Magnetic fields are PPE, planetary protective equipment. They're a really great idea. So Mars not having a magnetosphere, forget it. Other planets that don't have magnetic fields, they are not likely to be considered ideally habitable. I think it's also pertinent to ask whether there will inevitably be life on Earth in the future. I reckon that we live on a very dangerous planet. There are earthquakes, and there are tsunamis, and there are meteorites. After all, look what happened to the dinosaurs. We don't see them stomping around today. Yet we know they existed. In time, there will be no more life on Earth. Now, please don't panic, because what I'm thinking of when I say that is several billion years from now, when our sun turns into a red giant, at which time its radius will extend larger than Earth's orbital radius around the sun. At that time, the smart money would be living on, say, Neptune, which would become a lot warmer by that time. Probably there will be life in 100 years from now, but it's not inevitable. But it is fair to say that life will one day end on this planet, even if not very imminently, we hope. But I want to turn now to how it all began. And I want to begin at nearly the beginning of time, the beginning of the universe. At about 1 second after the Big Bang, there was essentially only radiation and primordial plasma soup. It was so hot, so energetic, that matter couldn't coalesce into atoms. Temperatures were way too hot. But the universe was expanding and therefore cooling. And eventually, electrons and protons were cool enough to be able to form hydrogen. But there's more to life than hydrogen. If the universe only consisted of hydrogen, we would not be here. If we eat a balanced diet, then this is what we are comprised of, approximately. Varies from one to another, it varies depending on our diet. And so we do need all of these elements to have formed in the universe for life to happen itself. There are various means by which these have: nuclear synthesis within stars. Nuclear synthesis at the start of the Big Bang only gave us a smattering of the elements needed for life. But before I get to that, how do we get the basic structures of the building blocks of the universe to form? Well, I described this in my lecture entitled Structures in the Universe earlier in this series. And roughly speaking, the answer to that question is gravity. Inhomogeneities in that primordial plasma, which are manifested in the ripples in the cosmic microwave background, are the seeds of structure formation. If you have an inhomogeneity in the density of that plasma, it will collapse under gravity. Gravity only works in one direction. Little inhomogeneities, depicted on the left, will become big inhomogeneities on the right. Small overdensities in matter will become larger overdensity in matters. And so gravity gives us galaxies. Overdensities of matter collapse under gravity, and these coagulates of matter are called protogalaxies. Within protogalaxies, where the matter is sufficiently dense and sufficiently hot, fusion can take place if the temperatures are high enough. This releases radiation, and hence stars shine. Stars are critically important for the synthesis of elements in the universe. Stellar nuclear synthesis is a necessary process to have happened in the universe for life to take place. It's a necessary condition, but it's also not a sufficient condition. The kind of elements that can be synthesized in the interiors of stars won't actually give us all the elements, the trace elements, which are necessary for life as we know it, the sentient life that we're familiar with. Other elements come from nova explosions and from supernova explosions. And without those exotic, energetic phenomena taking place in the universe, we wouldn't have life at all. But planets do form manifestly all across the universe. I indicated that gravity was a key player. but it's not the only key player. The formation of protoplanetary disks, where disks of matter collapse under gravity, is not solely governed by one law of physics. The law of conservation of angular momentum is also critically important here. You see the spin of the matter being much, much faster in the centre than it is further out. And besides gravity, and besides the conservation of angular momentum, thermodynamics is also critically important for the formation of planets and disks around planets that subsequently form satellite systems or moons, much like the moons in orbit around Saturn. So I went into this in rather more detail in my previous lecture entitled Planetary Universe. Planets, exoplanets are a thing. They're out there. It's relatively easy to find them. The number of exoplanets that we now know is numbered in their thousands. But that's only searching a relatively small amount of space. And not only are there lots of galaxies out there, but there are lots of space itself is, to misquote Douglas Adams, is really big. And so I don't know whether you become more optimistic about finding life further out if you say, well, gosh, there are a lot of haystacks out there within which to maybe find a needle. But there's no doubt that the prospect of finding life outside of the solar system is really a very daunting problem indeed to solve. Outer space is big and amazing. The number of galaxies in the universe in the observable universe is up there at hundreds of billions. The number of stars in our galaxy, which is by no means one of the largest galaxies that we know about, is something like 100,000 million. How many stars have planets? Many. The numbers get to be big and daunting. How much of space have we searched already? How much is searchable in principle? A very, very tiny fraction. That little circle in the bottom left quadrant shows the fraction of our galaxy, only our galaxy, that has been searched thus far. At the end of my last lecture, entitled Planetary Universe, I reported that the number of planets that had been discovered were 5,005. It was a great landmark to have reached the discovery of 5,000 exoplanets. That number has gone up. It's now 5,035. So all the time, new planets are being confirmed. But you'll see the percentage of planets that are, in principle, have a sporting chance of being habitable is only a few percent, the terrestrial ones, the Earth-like ones. Forget the gaseous ones. I mean, they're very pretty and, massive and fascinating in terms of the physics of planetary formation, but they're not good hunting ground for life itself. So there's a lot of space out there, and this is a point that was pondered by the Italian physicist, Enrico Fermi, who was born in Rome, in Italy, in 1901. Fermi is often known as the father of the atomic bomb. He was known for his work on the first nuclear reactor, and he was a key player in the Manhattan Project in Los Alamos. But even at the time that he was developing, doing key work on the Manhattan Project, apparently at lunch one day, he just suddenly said, "Where is everyone? Where are they? If there are loads and loads of stars out there in loads and loads of different galaxies, and if there's life on at least one planet, then how come there isn't life on loads of planets? And how come we have heard nothing from anyone as yet?" This is something that is known as the Fermi paradox. The fact that if it's out there, and if stars and galaxies are utterly numerous, surely we should have seen any extraterrestrial beings. Surely they'd want to talk to us, wouldn't they? After all, we're such lovely people. That's the Fermi paradox. Well, Fermi's paradox was thought about by quite a lot of people. This the paradox came about really in the 1960s. And someone who did quite a lot of deep thinking about that was a chap called Frank Drake, who turned 92 just last Sunday. And he began thinking, just for our galaxy, can you encapsulate and attempt to quantify the probabilities, or if you want to call it prejudices, which govern, do you or don't you believe in Fermi's paradox? Are you startled that extraterrestrial life hasn't got in touch with us yet? And so Drake came up with an equation which attempts to quantify those probabilities and prejudices. So this is what's known as the Drake equation, where n on the left-hand side of the equation is the number of civilizations in our galaxy that we might be able to communicate with. So this would exclude planetary systems orbiting stars sort of the far side of the galactic centre, where there's so much dust and all the rest of it, you'd have trouble with your line of sight getting you a clear signal. So just think about the ones that there's a good line of sight to in principle. And now think about, well, you know, what's the formation of stars in the Milky Way? How many new stars are born in the Milky Way per year? How many planets are likely to be formed around those? Of the new stars that form in our galaxy, the Milky Way, what fraction of those have planets? I'll come back to this point in a minute, but I think of all the different quantities that I'm going to describe in the Drake equation, this one here, F sub p, the fraction of stars having planets, is probably the most well determined on the basis of having searched that tiny little fraction of our galaxy so far for the existence of orbiting planets round stars outside the solar system. Once you've quantified the fraction of stars that are formed each year and the fraction of those stars that have planets orbiting around them, then you want to think about the fraction of those planets that could support life. And I've already ruled out the gaseous planets and some of the others where they're too close and too hot or too far away and too cold. N sub e captures that. F sub L is the fraction of these planets that could go on to support life. And so that is where you feed in the kind of chemistry that you need. Enough oxygen, but not so much oxygen that you poison everyone. That's then multiplied. So all of these quantities are multiplied together to give us n, the number we expect, over on the left. But then Drake goes on to say, bear in mind, Enrico Fermi's paradox was, where is everyone? Why haven't they got in touch with us? Why haven't they talked to us? We're such lovely people. You have to then feed into that, of the fraction of planets that can sustain life, which of those can sustain intelligent life, sentient life, life that's capable of developing technology that could communicate with other people. And that's encapsulated in F subscript I, the fraction of planets that will go on to support intelligent life. But it's not enough to just be intelligent. After all, the ancient Greeks, the ancient Chinese, the ancient Indians, terribly intelligent, but they didn't have radar, even though they were intelligent. So we need to factor in the fraction of intelligent civilizations that will go on to develop the kind of technology that is detectable here on Earth. And then finally, the other important factor in Drake's equation is the length of time for which the particular planet that's sufficiently advanced that its technology can release signals that are detectable here on Earth, that time is finite. Just as life on Earth could end, will end in 6 billion years, so the duration of time for which any planet will be able to emit signals is similarly finite. And so we have to multiply in that that duration of time, that fraction of time, if we want to get back to what is n. I'm sure everyone in the audience is thinking, goodness, that doesn't seem a very well-known number, and that one doesn't either, and goodness, not many of them do at all. Like I said, f sub p is probably the one that we can hope to quantify best. What's the fraction of stars that have planets around them? And I suspect that's a reasonable fraction of unity. But all of these other factors here, I suspect, could be rather less than unity, in some cases a lot less than unity. Note that if any of these factors were equal to 0, the whole lot would be 0. We do not know what the value of these parameters is. But if you're an optimist, then that will cause you to say n is not 0. If it is not 0, let's go out searching for life. And let's think about the kind of life that might be searched for. There's no doubt that here on planet Earth, life can persist in extreme conditions. This is not life itself, but that I'm showing you, but this is indicative of the very extreme environments that you can get here on Earth. These are some photographs that I took in Yellowstone Park, where it's now thought that in some of the extreme conditions of pH, of salinity, of temperature, and to an extent pressure, there are simple, relatively simple cellular life forms in existence, just as there are way down in the ocean in circumstances of extreme pressure. So life can exist in extreme locations, in extreme environments on this planet. So that might encourage us that life on other planets could exist, because maybe conditions don't have to be as ideal as I was saying earlier in my shopping list of creature comforts or desiderata for habitability. Maybe if you want to broaden it a bit to say, well, let's just see how much life is out there, even in extreme conditions, then maybe you stand a greater chance of detecting that. But just because there might be simple cellular life forms out there, just because there might be bacteria existing in extreme locations on other planets, could it follow, would it follow, that there would be sentient, intelligent life on that same planet? Simon Conway Morris has done some deep thinking on this, and at some point in one of these slides I'll be referring to his book that I think is a very stimulating read on this matter. If you want to consider whether life comes as standard in this universe, I think the best answer that you can give to that question right now is, we don't know. Observation of life on Earth is clearly a selection effect to those of us living on Earth. This is known as the anthropic principle. The observation of life on an exoplanet would be much more than just another data point. It would be very significant. It would make the difference between knowing whether life on this planet was unique, or if there's only one other, then that might well suggest that there's lots and lots of others. You could put in much more informed numbers into those factors in the Drake equation. One more data point would tell us a lot. But right now, we really don't know if we are unique or not. But if you're interested in these matters, as I mentioned a second ago, I really recommend Simon Conway Morris's book. He's a paleontologist in Cambridge. His book, Life's Solutions, Inevitable Humans in a Lonely Universe, is well worth reading. He reckons that sentient life is inevitable if, and only if, you get the right but very unlikely starting conditions. I really do recommend that book to you if you're interested in exploring, as it were, the biological side of life, which is a fairly crucial part of life. Let's go back to the idea of extraterrestrial life, and why are we so fascinated by the prospect of extraterrestrial life? A great many people are fascinated by extraterrestrial life. I used a little artistic license with that image. Why are we fascinated by the prospect? one answer is that it's very interesting to meet other people who are different from us. It's interesting to have relationships with people who are interestingly different from us. We learn new things, we gain new perspectives, we think in different ways. This basic human instinct, which desires an encounter with others, demonstrates that we, humans at least, are relational beings. We're predisposed to engage with others outside of our own circles. And so it is fascinating. It would be a wonderful thing to be able to pin down some of the numbers in the Drake equation even a little bit, because right now the factors in the Drake equation are as wide open as the universe itself. We've got very little determination of what those numbers are. So how do you go about searching for life on a planet? There are, in principle, two different ways. You can search for something known as biosignatures or biomarkers, which are markers of organisms that are respiring and functioning. Now, such an experiment has already taken place and has already found life here on Earth. And that's a good thing. That's a test of the technique. I'm talking about an experiment proposed by Carl Sagan. He wrote a letter to Nature around the time of Elizabeth II's Golden Jubilee, around 30 years ago, in relation to the Galileo spacecraft as it flew past Earth en route to Jupiter, which it flew into headfirst some years later. The Galileo spacecraft prompted Carl Sagan to propose this novel experiment, which wasn't the primary goal of the Galileo space mission. But his proposal was, let's use the Galileo spacecraft to look from space back at Earth to see whether we can see signs of life. Happily, you'll be pleased to hear that it did indeed find those signs of life. The spacecraft found high levels of methane, that's CH4, so maybe that gives you evidence for the existence of cows, and oxygen and CO2. And the ratios of these give you confidence in the fact that photosynthesis is taking place, the process that living plants undergo. So all of these particular signatures of molecules that are present in Earth's atmosphere are what are known as, are examples of biosignatures. The prospect of even more biosignatures, biomarkers that are even more complicated organic molecules would of course be much more stringent indicators of life on Earth. I conjecture that if ever you found the caffeine molecule in space, which some of us might say is necessary for sustaining life, at least when we're tired, would be quite a significant discovery of a biomarker. This experiment was repeated with the OSIRIS-REx spacecraft, which flew past Earth in 2017. It found that there was still life on Earth. This is a good thing. I should say, by the way, that OSIRIS-REx, the successor to Galileo in this context, the name OSIRIS-REx stands for Origin, Spectral Interpretation, Resource Identification and Security Regolith Explorer Mission. I conjecture that that's a classic case of the name of a mission designed by committee. Incidentally, regolith is a pretentious word for dust and gravel. But anyway, back to what the OSIRIS-REx spacecraft found. It found those same biomarkers, but it also found that atmospheric levels of carbon dioxide and methane had increased significantly. This is not good. This is not good for the survival of people on planet Earth. But I'm slightly stepping out of my field here, but I'm very happy to tell you that Gresham has recently announced the appointment of its new Gresham Professor of the Environment, which happens to be my colleague in Oxford Physics, the atmospheric physicist Miles Allen. And he tells me that his second lecture in his series starting in the autumn is precisely going to be talking about studying the greenhouse effect on planet Earth from space. So do look out for his lecture entitled The Atmospheric Physics Behind Net Zero. But if biomarkers are one way of looking for life, but potentially they have the drawback that they don't necessarily tell you about intelligent life, depending on whether you think cows are important or not, perhaps a smarter move might be to search for not biosignatures, but tech signatures. So tech signatures are all about signatures of a technologically advanced civilization. A technologically advanced civilization might be a civilization that's invented radar or digital signal projection or television or radio. These are the kinds of things that we hope to eavesdrop on and detect when we're talking about tech signatures. Now, there are about 15,000 star systems within about 70 light years of Earth. So if you think about those 15,000 stars for a moment and think about planetary systems which may or may not, but probably are, in orbit around the majority of those 15,000 stars, if they had really, really good radio telescopes or even really brilliant optical telescopes, then what they would see, at least 69 years, corresponding to 69 years ago tomorrow, would be the first ever broadcast of the coronation of a monarch. But that would be only for those stars closer than 70 or 69 light years away from Earth. But now think about it the other way round and think about, from the vantage point of radio telescopes on planet Earth, what tech signatures might we see? This is the Lovell Telescope, which is part of Jodrell Bank in Cheshire, and a visit to its Discovery Centre is highly recommended now lockdown is over. I talked quite a bit about the benefits of doing astronomy in the radio part of the electromagnetic spectrum in my previous lecture in Cosmic Concepts, in the Cosmic Concepts series entitled Watching the Radio. And one of those key advantages is that radio waves can penetrate through clouds that we're covered with a lot of the time in England, but also dust that's intervening along our line of sight to the galaxy. Highly recommended in this particular context is the movie Contact. I think this is a great movie, but it does get certain things wrong about the way in which we do radio astronomy. We don't listen. We do use telescopes to search all kinds of phenomena, energetic phenomena in the universe, but they have been used, especially recently, quite a bit in the context of searching for extraterrestrial intelligence. And now, a substantial fraction of quite a few of the world's best radio telescopes has been dedicated purely for searches of tech signatures which would correspond to intelligent life, industrially advanced life on another planet. Of course, the danger of looking for signals arising from instruments comparable with our own is that you might just be detecting yourself. And so it has to be said, a huge amount of calibration, verification, digital signal processing is really important for this. I would say it's an even bigger software challenge than it is a challenge in any other way to be able to definitively detect and confirm a tech signature of extraterrestrial intelligence. That's the Very Large Array Telescope, which actually featured in the movie Contact alongside Jodie Foster. And this is the Parkes Telescope in in Australia, which featured in the movie The Dish. You can see that telescopes do feature quite a lot in movies. And this played a huge role in the Apollo landing, of course, but it's playing a huge role today in dedicating a fraction of its time to the search for extraterrestrial intelligence. This is its dish, and the dish can slew around to look in lots of different directions all around the sky. This is its top end, containing the receivers, and these are steps that you can walk along. So that dish can slew round, so it's pointing reasonably closely towards the horizon, and then you can step onto these steps and walk all the way along, if you don't mind heights, all the way into the dish itself. And I was privileged to visit there some years back. I'm not an expert on cricket, as you might imagine, but it is just about possible to play cricket up there, but that is not the best use of this amazing radio telescope. It is much better suited for astronomical purposes. So what are some of the major projects for searching for extraterrestrial intelligence these days? Well, of course, the pioneering venture is known as SETI, the Search for Extraterrestrial Intelligence, which was pioneered and masterminded by Jill Tarter, pictured here, who really is the person that Jodie Foster's character is modelled on in the movie Contact. And this makes use of the Allen Telescope Array, a radio telescope in Northern California. One of the other new initiatives announced just a few years ago is known as Breakthrough Listen, which is funded by Yuri and Julia Milner. And this is the largest ever scientific research programme aimed at finding evidence of civilizations beyond Earth. It includes a survey of the 1 million closest stars to Earth, and it scans the centre of our galaxy and the entire galactic plane. It listens, or will listen, for messages from the 100 closest galaxies to us. It's a very ambitious project, of course. But they have high sensitivity. They are sensitive enough to hear a common aircraft radar transmitting to us from any one of the 1,000 nearest stars. So if they're out there, this programme will detect them. They could detect a 100-watt laser from 25 trillion miles away. But of course, it's not just a question of having really good receivers bolted to really big telescopes with large collecting areas. Innovative software and data analysis techniques are crucial to the success of this. Breakthrough Listen is all about text signatures. Breakthrough Watch is all about biosignatures. And they're looking to identify and characterise Earth-sized rocky planets around Alpha Centauri and other stars within just 20 light years of Earth. And just 3 years ago, this programme had first light on the Very Large Telescope in Chile using the instrument Visier, which is a collaboration between the Breakthrough Initiative and the European Southern Observatory. So it's potentially really exciting, isn't it? If they're out there, we might discover aliens. But just a minute. Remember how I started my talk? What is humanity's record when it comes to meeting different people, when it comes to meeting strangers? Humanity's record shows repeatedly that our reaction to other cultures is different is inferior, different is threatening. Try telling a cowboy to love an Indian. There are all sorts of racial and ethnic barriers that abound even today. The Good Samaritan today is interpreted widely as meaning help the stranger. It might be a really good idea to get practice in before we meet the aliens. So, what is our place in space? Are we alone? Are we the only intellectually alive species in the universe? Whatever is the answer to this question, whether it's yes, we are alone, or no, the universe is teeming with aliens, I suggest to you that either answer to this question will be revolutionary. I do hope that you have enjoyed thinking about the possibility of discovering other life in the universe this evening. Thank you.
So there's been a lot of interest online in non-carbon-based life, or life that's fundamentally different from what we know on Earth. If life can be structured in radically different ways, would life be possible on those planets that have high radiation, extreme thermal variability? What would the biomarkers be for alternate types of life? Are we looking in those ways?
Thank you. I think this is a really fascinating area, the idea of, for example, silicon-based life as being an example of non-carbon-based life. There's ever so much carbon in all of us at present. But could life exist that was based somewhat analogously on silicon instead? The answer to that is a definite maybe. I was particularly struck by the point about could that kind of life be resilient to radiation poisoning? Would it necessarily require a magnetosphere to protect itself from the possibility of radiation poisoning from the star it's orbiting around? That's a fascinating question. I'm not a chemist, and the answer to that question would really depend on the possibility of whether radioactive particles could trigger mutations in those silicon-based life forms. And I don't know enough about chemistry to know the answer to that question, but I think it's a fascinating possibility.
Do you need a planet to have life? Can you not have a life form in the universe, space?
Maybe. So in the context of life as we know it, I said towards the start of my lecture, and again somewhat in the middle, you can't have life as we know it being sustained on a gaseous giant. If you penetrate the surface of Jupiter, which is what the Galileo spacecraft did after it flew past us, there's no firm foundation on which life could be built. So I think the answer is not for life as we know it.
Is it the same? Is it the same answer for there are a couple of people online who are asking about life beginning in the oceans, and could there be life on a planet that didn't have this the rockiness that you were talking about?
I would have thought absolutely in principle in the following sense. Some people think, I don't think it's a favoured model now, but some smart people on the basis of very clear evidence have posited that life first developed, simple life forms first developed in very, very high pressure regions deep down in the oceans where there was a sufficient variety of chemical elements from the periodic table. And so if you ask the question, could it happen? The answer is, well, it certainly did happen at one stage in the history of our planet. What's being discussed as far as that is concerned on our planet is really the order in which it all happened at those early geological times rather than if it happened. So yes, definitely. But the question of if you have that sort of life, so non-land-based life, could it ultimately lead to sentient life forms? And that's why I'd really recommend reading Simon Conway Morris's book, who knows a whole lot more than I do about genetics and biology and paleontology, which is really what one needs to know, I think, to answer that question a bit more fully.
Thank you. Well, I'm afraid we are going to have to draw it to a close there. Thank you so much, Professor Blundell, for a really interesting lecture.